Hello and welcome to day 17 of my video journey to daily challenges. Let's begin our question. Okay, question 131, palindrome partitioning. Given a string S, partition S such that every substring of the partition is a palindrome. Return all possible palindrome partitions of S. So a partition of a string is essentially a slice. It's just that a partition could be many slices of the string, but the characteristic of a partition is that joining partitions of the string will actually end up in the original string. So for example, A, B. This is a partition where each element in this partition is itself a palindrome. Similarly, here, this is another partition where AA is a palindrome and B is a palindrome. Again, similarly to day 16 and 15, it seems like this is a situation where we have to go through all possible combinations of the original given inputs. So odds of this being another backtracing problem are pretty high. And it does seem to be the case because the hint here is that the constraint of the input string is very tight, only 16 characters. So a time limit exceeded is probably not going to be a problem if we go the iterative approach of finding all possible combinations. That being said, let's start the implementation. We've already, looking back at previous two questions, you could kind of remember what the structure of a backtracing program looks like. There's usually an answer there's a restriction, there's the backtracking, and then we call backtracking on something and return ans. In this case, the backtracking, we're probably going to, the condition on which case to backtrack will be if the substring of the start versus where we are right now, so first being this character, on the first level of recursion it would be this character. Then if this is a palindrome, then we move on to comparing. We move start to end and end to start plus 1 and compare if this is a palindrome, and etc. until we get to the end of the string. So here we're definitely going to have another sort of function called probably is palindrome with a start and the end and the actual string. Don't know how that's going to be implemented yet, although this is probably the easiest portion since I know that could just be passing in the string. However, yes, let me do that. I'm going to be passing in a string, and I'm going to say if len of s is equal to 1, return true. Then I'm going to say for I in S actually I can get away with doing this 0 to len of S divided by 2 if Si does not equal to S len S. So as you can probably guess, I want to save time by not iterating through the substring from beginning to end. So for example, if we have a string A, B, C, C, B, A, I'm going to be comparing the first and the second, the first and last, second and second to last, but I'm going to stop my iteration of start on up until here. So this is why divide by 2n. The problem here would be if we have a divide by a float here, because if this is a float, then there's going to be issues. So we're going to say int s len divided by 2 if s len minus I minus 1, because the index, the L is going to be non-inclusive. So if I do s len minus, if I take the index of S where index is s len minus I, the first I is going to be equal to 0, and that's going to be a problem because that's going to be an out of bounds. And here simply if we get that that this character is not equal to the symmetric on the opposing side, then return false, else return true. Very easy implementation of is palindrome. Now back to backtracking. So how are we going to structure this? Well, first of all, what will I need to start this? I need a point of where I'm starting. I need the and I need the current list, the current list of ones that I have already decided are palindromes from previous calls to backtracking. And here, let's say that if and condition and then recursive call. Again, if you want to see, this is the exact structure of this is exactly the structure that we've been using in previous questions. Start is going to be 0 and the current list is going to be none. We have a pass here. The end condition would be that if start is equal to n, then answer append cur list and return. Awesome. And the recursive call, where first on the first level of recursion, we only look at the first character, if that's a palindrome or not. Within it, in the case that it is a palindrome, we are calling back trace again, now with start equal to end. So for I, for, let's call it end, in range start, and this would be a len of s, which is just n. If we are a palindrome, if is palindrome s start end. If we're a palindrome, current list append s start end, backtrack this with start now being the end, and current list, and finally clean up after yourself when we go back down a level shallower. This would be diving into a level, so on the first level of recursion, we're just looking at this potential, the potential of this being a palindrome, then the potential of this being a palindrome, then potential of this being a palindrome. On the second level, when on the second level first instance is we've just looked at this, so we're looking at if this is a palindrome, and then if this is a palindrome. So here we need to clean up our current list up, and this should be good. Right off the bat, we're getting a maximum recursion depth exceeded by calling Python package. Okay, debugging maximum recursive calls is a bit tedious because it could be some edge case that I missed. So let's start. Some hints to look at here would be that backtracking is the one that's being called recursively too many times. So somewhere in here there could be a condition, or there is a condition that I am overlooking. Let's start by saying that no, this could be fine. Palindrome from start to finish. If this is a palindrome, then append right off the bat. Why not remove? Yes, this is already one. Okay. We have output equal to none. Why is that? Let's start with our print statements. If output is equal to none, that means that this is here is never getting executed. Let's print current list. See if current list is ever being populated. It is. A, and B. So B, okay, so this is our first hint. B is missing from this first instance, although it seems like we're almost on the right track. We have this is the first step of, or the first cur list that would be added to the answer, and then the first element in here is also present. Seems like we are missing this almost the next iteration, and okay, and I can already see what could be happening since we're treating since end for us is not the inside of this function, n is treated as the last element, or not the last element. It's treated as the the non-exclusive last element. So just out of curiosity, let's see what happens if we add this. And we are already getting somewhere. I can already see that. Yeah, what? Why is this not sufficient for it? Is it because I am actually writing a bit over? Expected answer. Cur list is being printed, and we're actually getting the right answers now. Okay, one thing that I'm confused about is why do I need to go over? Why do I need to go over the length of S? And should start at start plus 1 and go to, in our first case, go to 3. Would it actually be going to 3, or would it be let me actually run this once. It is going to 3, so, and length is equal to 3, so yeah, so this is non-inclusive. Yeah, okay, so yeah, since inside of this function we're treating n as the non-inclusive element to S, the right boundary of S, range in itself is non-inclusive. So this iteration is going to stop at 1 less than n. So to start treating n as the non-inclusive last element of within this function, here it has to be n plus 1. And this, the alternative here is to stay n here, but treat n end here as 1 plus n. But then here we would have to say start, yeah, basically, I'm sure you understand, but just the first call here would be 0, 0, start being 0 and end being 0. If we want this to be the non-inclusive in this sub S or substring of S, then this would be okay. If start is 0 and end is 0. But since this is non-inclusive, then we have to go a bit up, a bit higher. Sorry, it is still hard for me to sort of speak while I'm thinking, but now the question is why. Oh, yeah, sorry. We're getting the correct answers here. Why are they not being appended to the answer? A very common thing that I've experienced is lists in Python are always shallow copies. And so what I'm thinking here is even when we go into this function to print the correct answers, cur list at the end of the day gets a here, let me explain here. on the first level of recursion in here, when we assign to answer a current list, it actually assigns the state at which it assigns here a index or a pointer to the actual value of cur list. So cur list in the beginning is an empty array, and once we're doing this whole thing in here, there's only one instance of this current list. So we're doing everything correctly here, and as we can see, the standard out here is actually the correct answer. However, the append to answer here is actually, we're appending a pointer to the current list. However, the current list by the end of the day is just empty again because of this cleaning mechanism. If we were to remove this cleaning mechanism, the response here, the output, would be completely wrong. However, it would be populated. A, B, C, A, B, da, da, da. Yeah, so this is actually double of what we want. So a way to do a deep copy, this is a good way to remember, a way to do a deep copy of a list is to take its substring, just the substring with 0 and length of current list. And this should be good. Let's see if we, sweet, okay. Yeah, very, very simple solution. Very clean, very simple, and what I like about this is that this is specifically following the same structure of the previous backtracking solutions. If you look at my previous solutions, 16 and 17, please do that if you will. The structure is almost identical. Backtracking, the cleaning mechanism, and the appending, some weird condition by which is actually the only modification to the question, and then a returning answer. Since this beats pretty much everyone, I want to see what if, yeah, no, let's actually look at them. I know that another solution for this is dynamic programming, but I don't see why backtracing, or another name is DFS, because we are doing a deep dive into all possible combinations of the partitions. I don't see why DFS or backtracking is any worse, especially that clearly they are fixated on doing backtracking solutions this week. So yeah, yeah, guys, with that I'm gonna end. Stay tuned for next time. See you later. Bye.